So welcome. So today we're going to do this last section, which is basically diffraction and polarization. We've done interference of light, which depends on wave nature, and these are other properties which also depend upon the wave nature of light. And there's this curious thing, and that is when you pass light over a sharp edge, you do not get just absence of light and light. You get a very strange effect. If I have a razor blade and I fire a laser beam over it, I would see that I would get these, what's so-called fringes, dark and light fringes. And it's going to brightness here. And what we'd see is that the edge causes a kind of, if it's a circular aperture, there'll be a series of rings inside. And they'd fade off, but there'd be some rings inside. So near the edge, did you see this effect? And if I had a true slit, if I had a top and a bottom, I'd get these effects going both ways. So, kind of problem. If I want to look at this thing if I want to exaggerate this, then have a little aperture with a lot of edge around it, so use a pinhole. And what we see is patterns like this and like this. These are so-called diffraction patterns. This is also a diffraction pattern. Anytime you get in diffraction, it's a diffraction pattern. And because people like to study this, they came up with two ways of studying it. One was, we'll just put the aperture in front of a screen and photograph what we get. And that's so-called Fresnel. I know it said Fresnel, but it's French. So it's Fresnel diffraction. And we see that the minimums don't go to zero. There's still some light there on the minimums. If I move the pinhole long way away from the screen, or if I fool the optics into thinking I've done that by putting the right lens there, then I get this where there's the minimums go to zero. And that's called Fraunhofer diffraction. And optical people really get into what's going on with these things. I did a lab. I did an undergraduate project. We had to do undergraduate research. And I did a lab where the faculty member wanted me to look at patterns like this from different shapes. So rather than just using a circle, we also used triangles, and we used hexagons and stuff like that to see. And then he wanted me to mathematically, using an old mainframe computer, using iteration, but basically get the pattern that you got from theory and confirmed the two of them. Simple, do it on computer, do it in the lab, and go on. And the weirdest thing happened. I had this idea, rather than having these things machined, I would just paint them on a piece of paper, and then use. And back in the day, we used to use. You could take a photograph of writing, and then you would get a slide from it, and it would be kind of like reverse contrast. So I thought I'd do that for my aperture, just paint a black triangle and then photograph it. And then the photographer in our department said, well, actually, I can do you a kind of just inversion film where it just inverts it, So fine, okay. So I did that, and I got asymmetrical patterns. Like I got a bright line there and not such a bright line, and then a bright line there and not such a bright line, and a bright line there and not such a bright line. So there was a threefold symmetry, but not a sixfold symmetry. And the math said it should have been a sixfold symmetry. And I was like, oh man, I've discovered something really, I had no idea why it was. And when I had my Viva Voce exam, when I had my oral exam, the two people who were, the way that they evaluated this was two faculty members sat down and just quizzed you about what you'd done. You had to do a report, but they read it and then they asked you questions. And they didn't know what was going on. It was like, And I moved on, I graduated, and I remember that I had the picture on my wall for the longest time. And then I was at USF years later, and I was talking to some of the optical people there, and they knew exactly what had gone on. Optics is one of those weird subjects where it's everywhere, and the people who get involved in it really get involved in it. And there's not really a degree in optical engineering as far as I know. I don't know that there is one. I know that at UCF there's a centre, I think it's called Creole, I think it is, to do with lasers and the like. But it's one of those things where you can spend an entire career being an expert on optics, and you'll work in various areas, and it's a little world to itself. So. And some people just, visually, I just loved it. It was just fascinating to me, because you get these really strange effects. I'd like you to know the difference between Fraunhofer diffraction and Fresnel diffraction. I'd like you to be able to pick out which is which. So you'd like to recognize this does not go to zero, but this does. And I'd like you to know the difference in terms of the positioning or the lens and the like. Yeah.
So basically the difference between is that the Fraunhofer is either very far away from the screen or has a lens that gives that effect.
Yes, exactly. Yes, exactly, yeah. And, from a visual point of view, Fraunhofer diffraction, you actually get your minimums are zero, Yeah, cool. Okay, so now let's think about this thing. Let's say we have a slit rather than a circle, because it makes the math a bit easier. And what we find is that, and again, so now must be a really long distance, because I'm showing Fraunhofer diffraction, although there's no lens there. But basically, we can do a calculation, and we can prove to ourselves that m lambda, so this is the m going from basically, and so, okay, m lambda equals a sine theta, where a is the diameter or the width of the slit. M is the order. Okay, but this is a weird thing. This is the equation for destructive interference. So whereas before you learned m lambda equals d sine theta, and d was basically m was a number which went from 0 upwards, and the 0th order fringe, bright fringe, was 0, and the first order bright fringe was 1, and the second order bright fringe was 2. Now it's the first dark fringe is 1, and the first light fringe is 2. Second dark fringe is 2, and so it's a little bit confusing. So it's a different thing. It's got a different title on it. It's diffraction rather than double slit interference, but just watch out for that. I don't tend to ask so many questions about this these days, I've got to be honest. I'd like you to know it's there. I'd like you to know the effects of it. We'll use this bit later on for something very important. A consequence of diffraction is that point sources of light appear to be disks. We call them iridisks. And we see halos around things. And the more significant the diffraction effects, the more significant this is. How can you make the diffraction effects more significant? Have less aperture and more edge. Small holes will give you bigger diffraction effects. A nice wide telescope will have the diffraction effects. The diffraction effects exist, but there'll be relatively little contribution to what you're looking at. So they become less significant. But they do limit the resolution of your instrument. And we talk about diffraction-limited optics. And diffraction-limited optics are optics which are pretty good. So that all that you're living with, the thing that's stopping you from getting better, sharper images, is the diffraction effect. You're not limited by other things. And so the question is, well, how good is the resolution, you know? And so we have to look at these three images and say, well, you know, what do you think? Is this two stars that are relatively close together in terms of their angle to us? And yeah, that's clearly two stars. Nobody's going to disagree with that. What about this one? Well, it looks to me like one star. It could be two that are not resolved, in which case, even if I'm guessing there's two, I can't take that to the bank. They're not resolved, you know. And then, well, where's the limit? And the limit is something like here, which is just resolved. And what we say is, for each one of those point sources of light, we actually get this pattern, this Fraunhofer diffraction pattern. And we have this minimum and this minimum, like a black disk going around the bright center, like over here. And they are just resolved when the maximum of the green cross-section lies on top of the first minimum of the red one. When you get that, you say they're just resolved. If they're further separated, they are resolved. If they're less separated, they're not resolved or unresolved. So this angle, this minimum angle of resolution is really important. And we characterize instruments in terms of this. By the way, this is a bit of thinking, which is not limited just to optics. If you do can you see how if I have a mass spectrometer which takes a series of ions, a family of ions, they're all the same ion, and I send it into a magnetic sector, so there's a magnetic field, and because of the Q V cross B, I get a force at 90 degrees to the motion, and that leads to an arc of travel. And as we learned with the fine beam tube, if I give the particle more momentum or more energy, then it goes straighter, and if I give it more charge, it goes less. And so if I take a complicated thing like acetone and I crack it, I use a hot filament to break it into different ion fractions, it tends to break in the same places. So it's not haphazard. It tends to break into maybe 3 or 5 or 7 common bits. And so when I send that signal, those ion bits into my mass spectrometer, I'll get 7 peaks. And so might be a big peak for one, and a little peak for another, and a little peak for another, but I'll get 7 peaks. And it's like a fingerprint, a bit like a gas discharge spectrum for hydrogen. You get a fingerprint for that species. And it tends to be a peak on top of a background. And then you get complications. Yeah. Maybe when I breathe out acetone with a little bit of alcohol and some other stuff. So peaks begin to overlap. And they'll overlap more the worse the resolution of my mass spectrometer is. If my mass spectrometer is not very well resolved, I get broad peaks. And if my mass spectrometer is very well resolved, I'll get sharp peaks. And the broader the peaks, the more chances there are that things will overlap. So to get good resolution of chemistry, I want good resolution in my ion optics. But I've got to talk about this, and so they use actually very similar ways of talking about these things. They talk about, are these peaks resolved? What's the definition of resolution? What is how do I define my resolution in terms of mass to charge ratios, and how do I improve my resolution, etc., etc., etc. So what you learn, what I found was what I learned as a spectroscopist was carrying over to astronomy in terms of looking at instruments. And so you get these skills that are highly transferable. This little way of approaching something astronomers are not going to invent, or spectroscopists can second actually. Spectroscopists are not going to invent new stuff just for the sake of it. They're going to use the vocabulary and the learning and the way of approach that's been taught to them classically, and it's probably optics that they learned and carried across. So I'd like you to be able to recognize, I'd like you to know the criterion for what is just resolved, well resolved, and unresolved. So it's when the maximum of the green peak lies on top of the first minimum of the red peak. Then you're just resolved. Further apart, great. Less unresolved. So you can tell my old boss at UF, we were going to a conference in Baltimore, and he was a family man, and his way of dealing with that was he got a car and he loaded it up with students, and he drove starting at like 3 in the morning to Baltimore, just like drove through. And I was very unhappy with that idea. So I took my car and took a couple of friends, and we went like a day before. It was like the weekend. We left on the Saturday. I remember we stayed in Charleston, South Carolina, and kind of like a bit of a vacation, and then we went on to Baltimore the next day. So my boss, unexpectedly, because he thought he'd fill his car with students, had like a half-empty car, and he was like not so happy about that. I didn't realize. I just thought, hey, I'll drive there. I'll just go. Never thought about it. And then on the way back, we did the same thing. I drove my car and took the weekend to get back, and he drove straight through. And I was saying, man, I was trying to smooth things over a bit. So I was going, oh man, you must have been so tired when you got back after that long drive. Did the students drive at all? Oh no, it's my car, I drove. Man, you must have been so tired. He goes, well, you have to be a little careful, especially when it's dark and you're driving, because the tendency your body clock is trying to send you to sleep. So I said, what did you do? And he goes, well, what I did was I looked at the cars behind me. And he said, I would see them go from a single point source of light to 2 well-defined point sources of light as they got closer. And then I sped up to send them back to being a one source of light. And I thought, is he having me on? Is this this is one of those things where I would never dream of doing that. And I'm not sure it would keep me awake. But, there's the scientist, he's like, he's just gleefully looking at science in action, If we apply this analysis to a circular slit, what we find is that, well, if we apply it to just a slit, then what we find is that. But if we apply it to a circular slit, this is the one I'm more interested in because it comes up more often, then we find that our minimum angle of resolution is 1.22 because it's circular, lambda over the diameter. Diameter measured in meters, wavelength measured in meters, gives you an angle. So, if I have a choice between a big angle instrument and a small angle instrument, and I want better resolution images, sharper images, which one will I pick? Will I pick the big theta or the small theta? Which is better? Why don't we vote on that? Have you got? No, don't worry about it. Just shout it out. You want the small angle. So this is small angle telescopes are better than big angle telescopes. Small angle telescopes are wide. That's basically how you can tell. But and how small? They measure the resolving power of decent quality telescopes in terms of arc seconds. Arc second. Anybody know? An arc minute is 1/60th of a degree. So an arc second is 1,360th of a degree. So take a degree and divide that into 3,600 bits. And that's the resolution that they can tell. It's amazing, really, isn't it? So know that expression and be able to use it. Notice also, as my wavelength increases, so for the same instrument, the angular resolution number increases. So the instrument is less sharp. So the instrument tends to be, remember how it goes, V equals F lambda, and V's a constant. So as my frequency goes up, my wavelength goes down. So blue light will give you sharper images than red light will. And X-rays, X-ray. Well, there's a problem now. I've got to be careful now. There's a problem with X-rays because they penetrate through things. But in principle, the smaller the frequency, the bigger the frequency, the smaller the wavelength, the sharper the image. If I reverse that and go with radio waves, redder than the reddest red that you can imagine, radio waves can be kilometers across. Low temperature objects in space emit radio waves. High temperature objects in space emit X-rays and gamma rays. So there's a lot of low temperature clouds out there that emit radio waves. And there's also things like Saturn. Jupiter emits radio waves for kind of different reasons. But based on temperature, we can get radio waves emitted. Based on electrical activity, we can get radio waves emitted. See the difference between the two? So it's very nice to be able to look at radio waves, and so radio telescopes are great. Radio waves do penetrate the atmosphere. At least some of them do. Not all of them do, but some of them do. And so we can put the telescopes down on Earth. And so we say, well, we'll just use a big dish. But it turns out that if I take a big dish, even like some of the just big dishes that they build into the craters of volcanoes, they're just not big enough to make up for the problem with the wavelength size. And so they've started to link radio telescopes together. So they might have a telescope in New Hampshire linked with a telescope in Washington, D.C. And it becomes like taking a lens and just covering over or cutting out the middle bit. It still focuses light, just not as much light. So you get the advantage of having the wide lens in terms of resolution, and you're sacrificing intensity, but you're not having to build a dish that covers 100 million people's homes. You can. So that's what they do, and they've even got radio telescopes in Hawaii, and can link them to radio telescopes in the Caribbean, and they can basically get effectively a really high resolution image. So if you look at radio telescope images over the last 10, 15 years, they've actually been getting sharper, whereas before they were always these fuzzy blobs. Now they're getting sharper and sharper, which is really good. They can't just take a picture with one and take a picture with the other and compare them. The two detectors have to be connected either in real time, or they have to use time encoders, which are really high resolution time encoders. So they can almost detect photon by photon. It's almost detect it, instant by instant. And then they can compare the two data sets. So it's really quite fascinating what's going on. So radio telescopes have a problem because the wavelength is too big. And then bigger the diameter of the telescope, then the smaller the angle of resolution, which means you can see things that, angularly speaking, are close together. Cool. I'd like you to know that expression. It's sometimes called the Rayleigh criteria, and sometimes it's called the angle of resolution for a circular aperture. Okay, so next let's go back and look at, we did the double slit experiment, and that was interference. Well, now let's do a whole bunch of slits. Why stop at two? Like razor blades. When I was a kid, razor blades came in one edge, and you'd cut yourself with them all the time because it was a piece of steel you were scrapping down the side of your face. And then there was another edge. Then they kept brought out double blades, and they were shorter, and they were kind of like on little springs, so they'd move the contours. And I think I just bought a razor blade that was like 4 edges. And it's great. It shaves really comfortably, and you don't. It's been years since I've cut myself. And if anything, I should be cutting myself more because I'm getting old. I'm getting, But I used to have to use a shaving mirror. Now I just kind of like do it by feeling, and that's amazing. So we're back. So so let's have more than just 2. Let's go on and on and on and on. So we have a whole bunch of them. So what happens? Well, it's the same thing repeated, so we get the same equation. We just get actually better intensity and probably better resolution. And so we get d sine theta equals m lambda, the same equation we use for the double slit. And of course we have we have our old m values, 0 and then 1 and then 2. So the 0th order is 0 and the first order brightness is 1 and the second order brightness is 2. And I don't care about, so this is about resolution, and I suppose you should know what the things stand for, although, just know this is in the book, frankly. But this is the method. We have some kind of light source, and we have a diffraction grating rather than a prism, and we have some kind of viewing telescope, and we can read the angle from here. So, okay. And that gives us a basic spectrometer, which you may have used in chemistry. And so what I need to do is I need to show you how we're going to use this, because there's not an example in the notes. So let's do that. So come on. Yeah, go here. Okay. So let's make something up. Oh, didn't mean to do that. So go back. Go back. So let's say we have a light source coming in. And here's our diffraction grading. And let's say these are usually determined, they're usually characterized in terms of the lines per millimeter. So let's say there's 600 lines per millimeter. And then let's say that, well, what does this do? It causes interference patterns, bright and dark fringes. And we might get our first color top and bottom there, and then a different color will have a different solution. So if I look at, say, red and blue, there's my first order red, first order blue, and then I'm not going to care about that much, but I might also get second order pattern out here. I can ask about it, but it's just a repeat pattern. Okay? So for this, so M, I meant to do that in black, sorry. M, black. M is equal to 1, and M is equal to 2, and M is equal to 1, and M is equal to 2. Yeah? Let's just think about the first order. And we can measure an angle to the red and another angle to the blue. And I know the governing equation is m times lambda is equal to d sine theta, just like for a double slit. And, let's say that our lambda is 400 nanometers. Let's say it's blue light, 400 nanometers. I want to find out what angle this thing goes at. So find angle to first order 400 nanometer light. I say m lambda equals d sine theta. So m is going to be 1 because it's first order. And lambda is going to be 400 times 10 to the minus 9 because it's 400 nanometers. Equals d. Now d is equal to the repeat distance. Well, we have 1 millimeter, which is 1 times 10 to the minus 3, and I have 600 lines in that, so it's going to be 1 over 600 times 10 to the minus 3. Does that make sense? That's the mathematically the hard bit. That's the thing you've got to think about. It's 600 lines per millimeter, so we have 1/600th of a millimeter will be the space in between lines. So we get 1 times 10 to the minus 3 over 600 times sine theta. So sine theta is equal to 600 times 1 times 400 times 10 to the minus 9 over 1 times 10 to the minus 3. Yes. So sine theta is going to equal 240,000, I guess, times 10 to the minus 9 over 10 to the minus 3. So sine theta is equal to 24. That's 10 to the 4. That's not 19. That's 10 to the 9. That's 10 to the 4. And 10 to the 3 makes 10 to the 7. 24 times 10 to the minus 2, which equals 0.24, which is nice because it's less than 1, which is always pleasing. So theta equals sine to the minus 1 of 0.24. And can you look that up for me, please? It's going to be, about 11 degrees or 13 degrees or something like that. Or so many radians, whatever. 13.9. So that's 13.9 degrees. Cool. Do you want to know something? Do you want to do the next bit, which is kind of like, it's a little bit of an aside. If E is equal to HF, so E is equal to, what was that? What's H in numerical terms?
6.62 times 10 to the negative 34.
Hold on. Times F. Well, we don't know F, but F is equal to C over lambda, yeah? Which equals HC over lambda. Because C is equal to F lambda. So E is equal to 6.6 times 10 to the minus 34 times 3 times 10 to the 8 over lambda. 400 times 10 to the minus 9. So E is equal to, we're just going to do ballpark. So that's going to be 7 threes are 21. 4 into 21 is about, I don't know, 5 times. That's 5 times 10 to the minus 34, and 8 makes minus 26. And 10 makes 16, and that makes 17. I think that's right. Did I do that the right way around? I think I did that the right way round. But because it's 400, so I didn't do that right way round. It's 15 because of that. 400. So that would be, what's the units going to be? Joules, yeah. And if you want to go from that to E electron volts, what would you do? So 5 times 10 to the 15 over 1.6 times 10 to the minus 19 eV. Does the charge divide, literally divide the joules by the charge of an electron? EV, yeah, I guess it gets you the value. So what we're going to do, and I think next time, is we do a lab where we take a piece of diffraction grating, which probably cost about probably 10 cents to make. And we have a light source. The light source is the expensive bit. It's going to be like a neon tube type thing. That's hydrogen. Neon tubes are not that expensive anymore. And we're going to use a couple of markers, and we're going to find one of the energy levels for hydrogen using $20 worth of equipment, you know. And if you did that 100 years ago, maybe 120 years ago, you'd have got a Nobel Prize for it. But no one's going to care, because it's too late. But it's very nice. It's very nice to be able to do stuff like simple, you know, advanced science using simple equipment is always nice. Last little bit. So we know that light is E cross B, and we know that the E induces the B, and the B induces the E, so you'd actually need a medium for light to propagate. And if we draw our light, we can see that although there's a 90-degree angle between the E and the B, there's nothing that says that E has to be vertical or B has to be vertical. And so when you imagine photons coming towards you, like footballs coming towards you, they'll have a whole variety of orientations. I'm drawing just the E axis here, and you'll see that, you know, they're just all haphazard. No, who cares, you know? It's just an energy, it's just a package of energy, and it's... Then they started messing with crystals, certain crystals, and they found that, and they also had some, well, and there were also some minerals. Well, I've got to be careful here, historical. Anyway, what they found was they could mix some crystals, and the crystals did a really weird thing. They were like dark, transparent but dark crystals. What they would do is they would only allow the component of a photon through that was of a certain orientation. So if you imagine the crystal like that, I'm imagining these grains, these lines of stuff in the crystal. If the photon was lined up like that with this E field, it would get through completely. And if it was like that, it would not get through at all. And if it was like that, a little bit of it would get through that little component there. So you'd change the amplitude dependent upon that. And so you'd go from what's called unpolarized light to polarized light. All the photons at this point would have, they might be big or small, but they'd have the same orientation. Same frequency, not changing color, not changing wavelength, you're just changing kind of like the I suppose the intensity actually. Can you tell by looking if you're looking at polarized light? Absolutely not. So what's the point? The point is this. If I change unpolarized light into polarized light, and then I have a material, it's called an optically active material. Optically active materials, they kind of twist. So if there's the light coming in, as the light goes through it, the axis gets twisted. And so you go in vertically, you come out at 22 degrees. If it's thicker, you come out at 0 degrees. If it's thicker, you go out at negative degrees. It twists it. And some materials do this. And so they came up with a way of analyzing this behavior. So this is basically showing, so what they came up with was we'll have a polarizing crystal and we'll have an analyzing crystal. And if I don't have anything in between, I just put the polarizing and the analyzing crystal in line with each other, and I don't see much fall off in intensity where there's the double layer. If I have them at 90 degrees to each other, then I get opaqueness where there's the double layer. And if there's in between, then I see a little bit of fall off. But if I have an optically active material, especially if its optical activity changes from grain to grain, so now I have a situation where I have that bit's going to be optically active and that bit's going to be a different activity, and that bit 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 and that bit. So what happens is if that bit has a certain orientation of optical activity, and so does that bit, and so does that bit, I can set up my filters so those guys light up and the rest is like not so bright. And then I can turn the thing so that these guys light up and the rest do not, and so on. So I can see the optical activity of these different grains of material using this filtering system. And it's called, I think it's called Zelinsky imaging, I think it's called. And you can buy, on a microscope, you can buy this little attachment which goes on, which enables you to do that. And it's a great way of looking at minerals and the like. There's another thing, which is that if you take certain materials like cheap plastic, not expensive plastic it seems, but cheap plastic, like the stuff that your protractor's made out of, and you stress it, then you change the optical activity of that material in certain regions. And so you can see, if you're stressing it, you'll see these different stress fields come in. And you can visualize it using this system. So for complicated structures, especially back in the day before they had advanced computing, you could build a model of your cathedral and you could push on it and you could see where the walls are likely to crack and all that kind of stuff. So it's really quite useful. But the thing that really got this... Okay, so before I tell you about that, and there's a really famous law which is Maulis's law. And that's the intensity that you get out when you have a polarizer and an analyzer and there's nothing in between. The intensity you get out is equal to the maximum intensity, that's what you put in, times the cosine squared of the angle between the two orientations of the crystals. So if they're lined up, it's cosine squared of 1, which is 1. And if at 90 degrees, cosine squared of 0 is 0. Notice that cosine squared is not another number on your calculator. It's just the cosine and you square it. So why didn't they put down cosine squared? Because people would think it's the angle squared. So they decided to call it cosine squared theta. Yeah. But it's not like a different function. It's just get the cosine and square it. Okay, that's nice, it's academic and all that, but this is why these things really took off, this polarization really took off, and that is that you can polarize light by reflection as well. So not just putting it through a polarizing filter, but you can polarize light by reflection as well. If you come in basically at a large angle of incidence, remember, we always measure angles from the from the surface normal. So if you come in at a shallow angle, you may well, and you're bouncing off something like water or some reflective surface, a bigger refractive index, then you're likely to have polarized the light. So unpolarized light struck the surface, but only polarized light bounced off the surface. So if you go fishing and the light is bouncing at the right angle, all the glare is polarized. If you're in a parking lot and you're looking at a car in the distance and you're seeing glare from that car, all that light is likely to be polarized. Now, here's the advantage. if I go fishing, I could wear dark glasses to get rid of the glare, but it also reduces the intensity of the other bits that are not the glare, and so I can't see much. That makes the glare comfortable, but I can't see in the trees, or I can't see next to where the glare is in the water. And if I'm driving along and because I remember years and years ago, I got a pair of really dark sunglasses that were non-polarized, and they were like so nice on a sunny day. But if there was any kind of tree cover, I couldn't see anything because it reduced the low intensities as well. Whereas the potential for polarized glasses is that they only get rid of the glare. Because the glare has one polarization and you make your lens the other polarization, those photons don't get through. But the unpolarized light from the trees and the rest of the car, that gets through. So you're not diminishing that by very much, but you are diminishing the glare. So it makes it very comfortable. And for fishing, the big selling point initially was you could actually get rid of the glare and see the fishes under the water, you know. And it was actually, these were marketed to sports people initially. So this is called basically polarization by reflection, and there's a thing called the Brewster angle, which is basically the angle at which this effect begins. And all I want you to know is that there is a thing called the Brewster angle, and you don't need to know the equation, just know the Brewster angle that exists. And that's what put the polarized lenses on the market, and to this day, I mean, for a while, Polaroid, I think, had the patent for polarized lenses. And so people would talk Polaroids. My generation talked about having a pair of Polaroids. And it became like the Hoover for the vacuum cleaner. It became the go-to phrase, the trade name became the thing. And then that old pens don't last that long. They last for about 14 years. So after 14 years, everybody could pile in. And because Polaroid had the patent and the license, they could license it out. But because they had the dominance in the market, they could charge a very expensive amount for Polaroid lenses. And then when the patent gets freed up, what do? Do they go to the bottom like everybody else and try and make it as cheap as possible because there's competition? Well, they try and keep the name, don't they? So Polaroid glasses came down a bit, but not that much. And you could buy these other sunglasses, and they were also polarizing, but were they as good? As a scientist, they're as good, but as a consumer, are they as good? And then to mix things in, you got knockoffs that were actually just dark glass, and they weren't polarizing. And so to prove that they were polarizing, I think Polaroid and various other companies, on a pair of polarized sunglasses, you'd find there was a little paper bit with a little string on it, and there was a little piece of polarizing film, and you were supposed to look through the lens, and if you looked through the lenses and you twisted it and it didn't go black, then they weren't polarizing. Well, no one used to. If you weren't selling polarizing lenses, you didn't used to give the little thing. So, but they do a lot, and that was, there was tremendous number of these things were sold. I suspect they came out of the military. I suspect that you get pilots and they're like in this very bright environment, and I suspect that that's what it was about. But I might be wrong on that. Yeah.
What does N stand for?
Refractive index.
Refractive index.
Yeah. Cool. Okay. I think we're done.